Hello everyone, we are Group 31 and our advisor is Duskaya. The title of our project is Development of Rod-Based Intrapod Electrical Power Supply. My name is İrem Karaj, I am the team leader and my teammates are Fatih Özdemir, Nisan Uruç and Enise Feyza Kuzoluk. Each team member contributed equally and effectively throughout the project. In the first part of the presentation, I'll talk about the problem statement, system requirements, proposed concept and detailed design. Our first topic is needs identification and problem statement. Some system carried inside the pod may draw more power than the aircraft can supply. Therefore, a reliable power source that can operate independently of the aircraft's electrical system is required. Our goal was to develop a system that meets exactly these needs. According to this need, we define some key requirements. The system should have a compact structure to fit within standard pod dimensions. It should provide multiple output voltages. It must maintain stable output despite varying airflow and operate independently from the aircraft. And finally, high power capacity is an important design goal. This image shows the overall layout of our proposed system. Air enters through an adjustable intake and drives the turbine, where it is converted into mechanical energy. This energy is then converted into electrical energy by a generator. The required output levels are provided through power electronic circuits. The actuator system dynamically adjusts the air intake opening to stabilize the output voltage. Finally, this diagram illustrates all components of the system in detail. The system starts with the air intake. The incoming air passes through the rod system and the generator. With the actuator control unit, we adjust the flaps to keep the generator output voltage stable. On the right side, the voltage from the generator is delivered to the power distribution board, where it is converted into required DC and AC levels. That concludes my part. Thank you for listening.
Hi, I am Fatih Özdemir. I am working as a system engineer on this project. First of all, at the beginning of our project, we adopted the model-based system engineering approach and used the Capella program based on the Arcadia methodology. The operational analysis provides a high-level abstraction of the system's core mission. In this context, the air mass is defined as the primary energy source and the electromagnetic load represents the critical system requiring power. In system analysis level, a more detailed representation of subsystem responsibilities and their interactions is provided. The RAM air turbine block is decomposed into several functional segments. Here, it is modeled to generate mechanical energy by rotating the turbine of the air mass, converting the produced AC voltage to DC voltage, and obtaining the appropriate voltage values for the load. In logical architecture stage, the internal control logic signal flow and data exchange mechanism that support system stability and responsiveness are represented. Here, blocks were defined to increase the traceability of the system and the modeling was completed. The system design was simulated in MATLAB Simulink with all submodules. We can see wind turbine, generator, rectifier, feedback, inverter, and buck converter subsystem blocks. Here we see the feedback system we have made for the actuator control. Despite varying air intake conditions, the flap opening is adjusted according to the power demand of the load to ensure stable power generation with this feedback system. We designed synchron buck converter circuit using Altium Designer. We can see the schematic here. After the electronic board production stage, we completed our buck converter circuit by soldering SMD materials. By switching to MOSFETs with HTM, we obtained the voltages of 5 and 14 volts. In order to better understand and prototype the pod concept, we made a 3D design using the Fusion program. We implemented the design using a 3D printer.
Hi, my name is Nisan Uruç and I'm the hardware engineer of the team. I will present the testing process and demonstrate how our design meets the defined requirements. First, we identified two main test stages in our project: actuator control and output voltage regulation. The main goal of this test is to verify the compliance of the system with the design requirements. We conducted various types of tests, including Simulink-based modeling and voltage validation. We conducted an acceptance test in MATLAB Simulink environment to validate actuator control. The objective was to keep the generator output voltage within the 360 volt and 380 volt RMS range by adjusting the cover opening ratio. In the simulation, different wind speeds were applied to observe this system's response. This test was successfully completed. As seen in the simulation, at different bite speeds, the actuator adjusted the cover opening ratio and successfully maintained the generator output voltage within the desired range. In this part, we conducted an acceptance test for buck converter circuits. We aimed to see if different duty cycle values applied via the microcontroller could generate stable 5-volt and 14-volt output voltages from a 24-volt input source. This test was successfully completed. As seen in the photos, the buck converter generator stables 5-volt and 14-volt outputs as expected. This confirms that the power control unit performs correctly under the tested conditions. As shown, most of the requirements have been successfully met, including compact design, multi-output, and stable output. However, the high power capacity has remained below the desired level due to current prototype limitations.
I am Enise Feyza Kululuk. I am working on this project as an integration engineer. First, I would like to begin by presenting the cost analysis of our project. As seen in the table, our total cost is categorized under three main headings. These are component, equipment, and services. These include elements for the buck converter, lab devices, and services for PCB fabrication and 3D design. The total cost is shown at the bottom of the table. Now, let's look at the commercialization strategy of our project in 3 steps. The first step in our strategy is to promote the product by highlighting key features which reflect both technical and market value. As you can see here, our product have critical points like filling a scientific and sectoral gap based on wind energy and supports high power application. Our target users are primarily firms within the defense industries, especially rail platform manufacturer and system integrator. For the marketing phase, we plan to apply defense industry project support program and international conference. With the conference paper that we published, we have taken a significant step by participating in an international conference held in Romania. Our project has been designed with various aviation and military standards, including all of these standards. The certification process aims to obtain certification valid in Europe and the United States and the Turkey. And in this section, I will present the safety aspect of our system. Here, our system provides electrical, thermal, and mechanical safety through against leakage, short circuit, overheating, and physical impact. It's resistant to water and moisture. And here, in case of failure, it's switched to safe model. It's EMI complete and provides temporary backup power with a battery during turbine faults. Thank you for watching us.